We're now beginning the next chapter, chapter 29, which is on Faraday's law. This is, without a doubt, one of the most important and remarkable things, or discoveries, I should say, that came from the initial studies of electric and magnetic fields. Our first module here, 29.1, discusses Faraday's law and how it came about in its discovery. Faraday's discovery, as I recall it, he was actually doing an experiment in a class, and he had a loop of wire. He had a magnet here on the table. So he had a magnetic field B. He had a loop of wire, and this loop of wire was connected to a galvanometer. The galvanometer could detect currents and therefore would detect voltages. And he reached down, he just had these sitting on his table. He was getting ready to do a lecture, I believe, to his students. And he picked up the magnet and moved it. And when he did that, he noticed that the galvanometer jumped. Well, that didn't make any sense, because this was a magnet and this was electric current that would only arise from a flow of current that would come from a voltage. So he put the magnet back, it jumped again. Actually, the galvanometer goes to the center, it jumped one way and then it jumped the other way. Well, then he was really shocked. So he pulled it out, put it back, pulled it out, put it back. And each time he moved the magnet, moving it different directions, he found that he always generated a current through this galvanometer, a detector for the movement of electrons through the circuit. Well, how was this possible? Well, as I recall the story, he dismissed the class and began his discussion of this. And what he did in his experiments was he concluded that the flux that comes from this magnetic field, if it goes through this loop, either due to the orientation of the wire, in other words, I could move the wire, or the loop, or the magnet, in any way that this flux changes, so I get more flux or less magnetic field through this loop, then I get a voltage that follows. Even the motion of the source magnet can create that voltage. Thus, a changing magnetic field flux in a circuit can induce an electric potential or voltage. That is an incredible discovery, as you will soon see. It gives the possibility of generating electrical voltage and therefore electrical power from mechanical power. It means, for example, that we could take a loop of wire, have the loop come off here, and we could take this and put it on an axis and rotate it. How would we rotate it? Well, we could have a waterfall that came over and there were paddles here. Or we could have a steam generator, or we could have a horse turning this thing, or you could crank it by hand. But the point is, you make this thing rotate. And when you do that, you want to put a magnetic field. So let's put a magnetic field through here. So the magnetic field is coming out of the page. That's a B field. And here's a loop, and as that loop turns, less and less, and then more and more, a flux of the magnetic field is going through here. Then the question is, what kind of voltage do we get from that? Well, you can see why this is revolutionary. This means that this turning, this mechanical turning, induces a voltage. And the voltage that's induced, he found, was the following. The voltage that arises from this is the negative of the change in the flux through the coil with respect to time. Well, now what is the flux? The flux is the integral of the magnetic field over this surface. So this is minus d by dt of the integral of b dot d sigma. And so now we can write this result as, in a different way, we can say, what is the voltage? You'll recall that the voltage is given by the integral of E dot ds, a previous result that we had back when studying the electric field. So we can write this as voltage is equal to the integral of E dot ds E dot ds, which is equal to minus d by dt of the integral of b dot d sigma. Now this is over an open surface. This is over a curve that goes around that surface. So the voltage that is generated around this loop, namely the integral of E dot ds around this loop, add E and times ds and go all the way around that loop, is going to be equal to the voltage. We previously had that result. And it's going to be equal to d by dt of the change in flux through there. This is Faraday's law of induction. And one of Maxwell's equations from this part here. It is the fourth of the Maxwell's equations. And the reason that this is so incredibly important is it allows us to take mechanical work here by turning this, making a turbine here, using a coal plant, nuclear plant, waterfall, water pressure going through a dam, any way that we can turn this loop in a magnetic field, it will make a voltage. The voltage then can travel along and go to some distant point, like a town, and then that voltage can be used with a motor to make that work, that energy come back again. So it's a way of transporting energy from one place to another, or as we often say, power, from one place to another, only through a pair of wires without having any motion whatsoever. This was a revolution in technology that's just beyond belief, because it's the foundation of all of our electric power industry. I probably should add a simple example to that, and that simple example would be, let's imagine that we have a loop of wire, and this loop measures the distance A times the distance B. It's a rectangle. Of course, it's going to have two wires that feed off there. The wire goes all the way around here, it comes back out here. And so, therefore, what we can do is we can say what voltage will be accomplished if we take this, have an axis on it, and rotate it at a certain rate. Well, the answer is, if this has a magnetic field B, which is, say, 7 Teslas, and we look at this surface area, the surface area is going to begin as A times B, and then as this loop rotates, it'll go down to 0. So the voltage we're going to get starts out as a lot, then goes to 0, and it goes like a sine or cosine wave. And what we will have here is, depending upon how fast we rotate this, we can say, well, B is going to be 7. The area, the integral over d sigma, is going to be the area, so that would be the area, which would be A times B times the cosine of the angle. And the angle is going to depend upon what? It's going to be A times B times the cosine of omega t, where this is the angular velocity. And so this term on the right-hand side is going to be, give us voltage is equal to minus d by dt, well, we can forget the negative sign for right now because that just gives us the direction of the voltage. D by dt of the B times the A times the little b, which is the area, times the cosine of omega t. And we're going to take that derivative, and so that derivative will be the derivative of a cosine is a sine, and we bring out a factor of omega, so that would be b a b omega times the sine, and I'm forgetting the signs out front, it doesn't matter, sine of omega t. And so the maximum voltage that we're going to have, it's going to go from the maximum here to the maximum here, is going to be b times a times b times omega. And we have to figure out how fast we're turning that And so if our size of the two sides were 2 meters times 3 meters, for example, and omega was equal to 9, that's the angular velocity, then we would simply have b, which is 7, times a, which is 2, times 3, which is b, that gives us our area, times 9, which is omega, and this would be the magnitude of the voltage times the sine of omega t. And of course it's going to oscillate from this maximum value here, 2 times 7 times 3 times 9, up this way to down this way as oscillating voltage or alternating voltage.